Hello, everybody. So far, we have discussed some basic concepts of functions such as domain, range, evaluating functions, and analyzing functions both graphically and algebraically. Today, we're going to look at a few new concepts. So today, we're going to be talking about properties of functions. Okay, we're going to be dealing with some properties that we're going to use this year and next year. The first property we talk about are increasing, decreasing, and constant. Now, when we're talking about these types of properties, when we refer to this, we want to describe intervals. So basically, when you look from left to right on the graph of a function, let's say we have our function there. If a function is increasing, that means the y values are going up. Or the graph is moving in the upwards direction. If the function is decreasing, the y values are going down. There is a more complicated way with function notation to show this, but I think it's just easier to see. Decreasing is down, increasing is up, and constant obviously means y values stay the same. So in this graph, this section here, we could describe as decreasing. This middle piece here, where the y values are staying the same, is constant. And this piece here, we would describe as increasing. Just a little side note, in order to describe our intervals where the functions are increasing, decreasing, or constant, we're going to be using open intervals, meaning we're going to use parentheses to describe our intervals. So that concept behind that, or the idea behind that, is our endpoints of each interval are not included, okay, because the function is neither decreasing or increasing at that specific value. Another thing we're going to talk about in this topic today is relative max or relative minimum values. Turning points on the graph can be called local max and local mins, or relative minimums and relative maximums. Remember, in order for it to be a relative max or a local max, etc., it has to be a turning point. Okay. So we're definitely not going to include sorry about that. We're not going to use endpoints when we describe these values. We're only going to consider where the graph turns. A relative minimum goes from decreasing to increasing, and a relative maximum goes from increasing to decreasing. So on this graph here, this point here would be a relative or a local, so expect to see either word. Yeah, this would be a relative min. This would also be a relative min. So you can have more than one relative min on a graph, okay? Because when we're describing relative mins, we're talking about in relation to what's around it. So in this case here, I go from decreasing to increasing. Over here, I go from decreasing to increasing. That's how we make our decisions. And this guy up here, when I go from increasing to decreasing, this would be considered a relative max. Okay, so really, really important that these are turning points in the graph. A relative maximum or a minimum value is referring to the y value of the function. Okay, so when I ask you what the relative max or the relative min is, we're going to really use the y value. Okay. We are going to discuss this more in calculus. When we deal with word problems, it might say, when does it occur? That would be the x. What it is, that's the y. For our couple of examples here, we're going to describe the intervals where f of x is increasing, decreasing, or constant. Then we want to identify any relative maximum or minimum values on our graph. So in this first case here, our function is going to be increasing anytime it's moving in the upwards direction, which is that interval right there. So you could say, and if we look at this, this would be -3. So our function is increasing on the interval -3 all the way to 0. And notice again, I'm using those parentheses. Our function is decreasing anytime it's moving in the downward direction. So we're decreasing here and we're decreasing there. And if I look a little more closely, that would be probably about -5. Not a perfect graph, but that's okay. So we're decreasing from -5 to -3. And we're going to union that or end 4 to 6. And our function is constant in this section here. And that occurs on the x-axis from 0 to 4. And remember, our relative minimum value is going to be where our function goes from decreasing to increasing. So I'm going to have a relative min at that point there. And that is going to occur at y equals, well, that value is 2. Okay, because remember, the minimum value is the y value. And our relative maximum, in this case, I actually don't really have a maximum value because I don't go from increasing to decreasing or decreasing to increasing anywhere on the graph. I'm sorry, I don't go from increasing to decreasing anywhere on the graph. So there is no maximum value. We do not include endpoints. Just as a little side note, sometimes with our relative mins and maxes, you could write it as an ordered pair. Okay, and I think on some of the answer keys, I have done that. But we want to kind of understand that the minimum value is referring to the y value itself. In the next example, we're going to describe increasing, decreasing, constant, any maxes or mins. So if I go back to my picture and I want to start off with increasing, my function is increasing on that interval and again on that interval. So we would say from -∞, because I don't have a dot now, so I'm just going to assume we have arrows. -∞ to -1. And it's going to start increasing again from 1 to infinity. And then our function is decreasing on this section here. And that would be on the x-axis from -1 to 1. Our function is never constant, and that's okay. And we're going to have a relative min when it goes from decreasing to increasing, or from our lowest turning point. And our relative minimum value is the y value. And our relative maximum is where I go from increasing to decreasing. So our relative maximum value on this graph is 2. Okay, and it refers to, that's why it's also local, because it refers to what it's around. It's the highest point of what it's close to. Today, we also need to talk about even and odd properties of functions. Now we say a function is even if it's symmetric with respect to the y-axis. Okay, so in other words, if you fold it right on the y-axis, it's going to be identical. An easy way to see this is if you remember your transformation rules. Okay, when we reflect through the y-axis, xy goes to -xy, right? We negate the x value. In function notation, we show this as f of x equals f of -x. And It's just really, if you think about it, if we think just with the number f of 2 equals 4 and f of negative 2 also equals 4. Okay, so with numbers, sometimes it's easy to see. We're going to actually be doing this with algebraic functions, so it's going to be a little bit harder, but always just think, is it symmetric with respect to the y-axis? Our odd functions are symmetric with respect to the origin, and the transformation rule there, when we reflect through the origin, is xy goes to negative x negative y. So in other words, this point here, 2, 8, if we were to reflect that through the origin, it would go to negative 2, negative 8. I'm not sure if I'm going to show you this with your function notation right now because it is a little bit confusing. Visually, when we're looking to see if something is even, odd, or neither, all we have to do, if we have the graph in front of us, is look at the picture. So if we're looking here at this graph, if I want to know if it's even, odd, or neither, I think an even function, y-axis, odd function with the origin, and neither is if I see no symmetry. So when I look at example A, it's easy to see that this is symmetric with respect to the origin. No matter where I go, if I fold on that line, it's a mirror image. So this is an even function. In example B, if I'm looking for symmetry, I don't really have it. If I'm going to fold on that line, it's not a mirror image. So this is neither. And for example C, when I look here, I kind of can, like, if I kind of pick out some key points here to kind of look at, I notice if I reflect through the origin, and even if I took a different point, I see that reflection through the origin or symmetry with respect to the origin. So this function here would be an odd. Now, while it may be easy to determine whether a function is even, odd, or neither when looking at the graph, we also have to be able to do this algebraically. And when we do it algebraically, we're going to use the actual function itself and look to see what we get. So when we're dealing with, if we want to show a function is an even function, we want to show that f of x is the same thing we would get as f of negative x. And if we want to show something's an odd function, f of negative x is equal to the negation of f of x. And just as a reminder, or something to help you out, when we're finding f of negative x, we just have to change the sign of our odd powers. If you go back to the first day while we were doing function notation and we practiced f of negative x and negation of f of x, that's where we were leading to. We were leading to examples like this when we can use those practices while we're trying to determine if a function is even or odd. So in these examples, we're going to determine if the functions are even, odd, or neither, and we're going to show our algebraic analysis to justify our answer. Okay, so we want to justify answers now. So when I'm doing these types of problems, basically what I'm thinking in my head is, if a function is even, that means that f of x equals f of negative x. So the first thing I'm going to do is I'm going to plug in or evaluate f of negative x, find that function, and see if it matches the original. If it matches the original, it's even. In this case, f of negative x, when I plug that in, and remember, all we really have to do is change the signs of the odd powers. Okay. So now, does this new function match the original? If it does, it's even. This one does not. So this function is not even. So the next thing we would do is we would test if it's odd. Now, if it's an odd function, f of negative x is going to equal the negation of f of x. We already have f of negative x in the line above. This is f of negative x. So now we're going to find the negation of f of x and compare those two. When I negate f of x, I wind up with negative x cubed plus 3x. Remember what we're comparing. Now we're comparing this guy with this guy. These two match, so this function is an odd function. Let's try example B. Remember, always start with even. So I'm going to start by finding f of negative x. Negative x squared minus 5. So f of negative x equals negative x squared is going to be x squared. Even if you want to kind of do this, does f of negative x equal f of x? Now I just look at them. Did what I get there match that? Yes, they are exactly the same. So this would be an even function. And you could stop because it's not going to be an odd function if it's an even function. In our next example, I start by finding g of negative x. So I have negative x plus the absolute value of negative x. And if I would go to evaluate this, this just becomes negative x. What's the absolute value of negative x? It's the same thing you would get if you evaluate the absolute value of x. So does g of negative x equal g of x? No, right? That does not happen. So it's not even. I'm going to negate the function now. So in actuality, we're doing this. And this equals negative x minus the absolute value. So now I'm going to compare these two, right? Does g of negative x equal negation of g of x? When I look at those are not the same. So it's not odd. So this function is neither. It's okay to get neither, don't get scared. Okay, a function doesn't necessarily have to be even or odd. In the last example, again, we're going to start with the same thing. Find f of negative x first. So everywhere I see an x, I'm substituting negative x. If it's an odd power, I'm just really changing the sign. Negative 3x cubed plus 2x over negative x to the 5th. So does this function here match this function here? No. It's not even. So now I want to negate my function. So remember, negating the function means you're multiplying by a negative 1 out front. This one's a little tricky because we want to remember when we multiply that whole thing by negative 1, we're really multiplying by negative 1 over 1. So we're only going to be changing, the signs of the numerator. Now when I look at my answers here, I feel like I did something wrong. Oh no. Negative, I'm sorry. I feel like I did something wrong with my math because I looked up too much. Negative 3x squared plus 2x, negative x to the fifth. Negative 3x squared plus 2x over x to the fifth. Oh, I did make a mistake somewhere. I'm so sorry, but I don't feel like recording this video all over again. So I have, oh, I see my mistake. Okay. I did make a mistake because I didn't check it carefully enough. So pause for 1 second. I mean, just take a deep breath here. And I'm so sorry. I see where I made my mistake. Wasn't so easy to see. But up in this example right here, I just needed to take a closer look at it. If you look at that negative x to the fifth on the bottom, okay. In math, sometimes we don't like to have the negative on the bottom. So if I was to divide through this, this becomes 3x cubed minus 2x over x to the fifth. And then these two actually match up. These two actually match up. F of negative x matches f of x. So this is actually an even function. Okay. Although we didn't have to really do the odd test because we already found out that it was even, doing the odd test brought up a good thing that some of you, you know what I mean, which is negating the function. When you negate a fraction, be careful only to negate the numerator. So if you have to do this in the future. So when you negate a fraction function, only negate the numerator. So my mistake was actually a blessing in disguise. All right, moving on. Last thing we're going to talk about today is the average rate of change. Okay. Hopefully you guys remember from your algebra class, from your geometry class, when you're finding the average rate of change, you are finding the rate at which the y values of the function are changing compared to the x values, right? We know this as slope. So if we think about our previous courses, okay, right, you know, we're going to be finding the average rate of change of a function over a given interval. So we're really going to be, I would describe some interval for you. We're really going to be finding the slope of what we call a secant line. So we know the slope formula to be y2 minus y1 over x2 minus x1. In this case, this is your ordered pair x1, y1, and this is your ordered pair x2, y2. Okay, that's how you guys are used to seeing it. When working with functions, when we describe the average rate of change, okay, we're going to want to try to use it as a formula. So if we want to find the average rate of change of f of x between x equals a and x equals b, I want to try to get you guys to be able to express this with more function notation. So if a is my x value, what point would be on the curve? The y value could be expressed as f of a. And if b is my second x value, my y value is going to be expressed as f of b. So if we were going to rewrite our slope formula using these 2 points instead, okay, our average rate of change formula becomes, remember, it's just the slope of a secant line. It becomes y2 minus y1 f of b minus f of a over x2 minus x1 over b minus a. And we want to try to start to show our substitutions into the average rate of change formula because we're going to really be using that concept next year. I'm going to ask you to find the average rate of change for the function f of x equals 3x squared, first from x equals 1 to x equals 2, and then on the interval 1 to 7. So I tried to switch up the way I asked your questions. Remember, average rate of change for this function. So if I want to set up, and some teachers use average rate of change to express this, I usually just go with slope of secant. So the slope of the secant line, or the average rate of change, this is my A and this is my B. So when we're setting this up, it's going to be f of 2 minus f of 1 over 2 minus 1. And now what we have to do is we have to find f of 2 and we have to find f of 1. So we plug them into the function. 12. So we're going to have 12 minus 3 over 2 minus 1, which is 9 over 1, which would just be 9. On the interval 1 to 7, again, now I gave you the information a little bit differently, but it's still going to be the same. Slope of a secant equals f of 7 minus f of 1 over 7 minus 1. F of 7, f of 1, 3 times 7 squared, 147. 3 times 1 squared equals 3. 147 minus 3 over 6. If you plug that into the calculator real quick, you're going to get 24. Okay. And basically, just before we end, let's just talk about what we just found. If we look at the function 3x squared, it's just going to be a steeper parabola. We just found from 1 to 2, we found the slope of that line. And then we did from 1 to 7. And again, not a great picture, but if you notice, that slope is going to be much steeper. Okay, so we just found those two slopes of the two lines that connect the 2 points on the graph. Okay, and that's it for today. So practice, do your homework, and we will see each other soon. Thank you. Bye.